Welcome to another RDWorks Learning Lab. Excuse me sipping my coffee because it's pretty cold in here and it's nice to have something warm inside you. Now today we're going to go back onto the subject of photo engraving, but the difference is that we're going to do it on a different group of materials. Now it's a family group of materials which loosely we would call stone or minerals. But there's a wide range of materials and material properties within that mineral group. I don't know quite how this is going to turn out. Like many things I do on camera, this will be the first foray into some of this stuff. Now, I'm not a geologist. It was a subject that slightly tempted me when I was much younger, but the prospect of climbing mountains and diving down to the bottom of the sea was perhaps not as tempting as it should have been at a young age. And so I plumped for engineering and, well, look where that's got me. Retired, grey, but happy. So before we start going into the photo engraving side of it, we need to do a little bit of exploratory work on these materials because we don't know whether they're, for instance, explosive, whether they're flammable, whether the fumes that come off of them or the dust that comes off them is dangerous. Those are the sorts of things that we're going to take a look at before we even start the photo engraving, because we don't know whether this stuff will mark. The main requirement for photo engraving is a good contrast, i.e. a binary material which, when you damage the surface of it, is a significantly different shade to what the natural surface is. Now, that was obvious when we were doing wood or paper, because we had white paper and brown or dark brown dots. That was a good contrast. I have dabbled a bit with slate in the past and not got very good results, but this time I've got some better quality slate to work with. Now, I'm extremely fortunate that not very far from where I live I have a specialist company that deals with upmarket worktops and cladding for bathrooms and floors. I visited them a few days ago in an attempt to try and find some maybe offcuts of material that I could use for this demonstration. Now, I've been extremely lucky, and as you can see, I've filled my machine here with a whole variety of materials that we're able to experiment and play with. I mean, I don't think there'll be anybody that doesn't understand what this stuff is. I mean, this is just roofing slate. But this is, if you like, one of the lowest of the low materials that we might be able to use. It's something called a foliated metamorphic rock. It's not really a rock, but it's basically mud, very fine clay mud. Now, if you look around at slate, you'll always find little crystalline pieces on the surface, little shiny pieces on the surface, and sometimes some goldy pieces. Now, these are all the same material, and it's a material called mica, and it is the mica that gets embedded in this material that causes it to be a flaky material that you can just break off into layers. So it isn't just the sedimentation of the mud that's caused the layering, it's also this mica. But basically this is sediment that has been, the technical word is subducted. It's been driven underground by movement of the earth, and as it dives underground underneath mountains and rocks, the pressure on it gets greater and greater, and the temperature goes up a little bit as it gets lower into the ground. But it changes into this petrified mud. The next weakest group, I suppose, of materials is something like this. Now, this material here is something called limestone. This is the good polished face, and this is the underneath face, which is in its way a little bit more interesting. You can sort of see a bit of a seashell there, and there's various other blobs in here which are, it could even be things like bits of coral, and it could also be fish poo. It's all been compressed down onto the seabed, and this is something called calcium carbonate. Basically, it's the same stuff that you get collected around your taps, that white lime scale. Well, these are limestone as opposed to lime scale, and this has then been again subducted underneath rocks, subjected to several thousands of tons, and low temperatures to turn it into a stone. The next stage on you might recognise as marble. Now you may or may not be able to see, depending on how the light catches it, but there are thousands of little teeny weeny crystals in there. This has been driven far underground and it's been subjected to heat as well, and the high temperature has recrystallised the limestone into a different material. It's the same material but different crystal structure. And here we have a thick piece of Italian slate. Now slate comes from all over the world, including Wales, but Wales is not a big producer of slate. It's very expensive slate from Wales, and there are far better sources around the world for slate. Now, not all slates are the same, and I hope that we might be able to see that later on, because, as I said, one of my early forays into slate told me that some of it was basically little more than congealed mud, and it did not yield a very good contrast. Now, these materials are made up mainly of a material called feldspar. There's some mica in here as well, and also quite a bit of quartz. It's the material that you probably will recognise as sand. Those chemicals have been bonded together by being exposed to a lot of heat beneath the Earth's surface. 700, 800, not quite melting point, which is probably 1,000 degrees C for volcanic rock, but very close to volcanic sources or very deep from within the Earth. And if we look at the edge of them, you can see this very crystalline structure in there. And so the industry involved with these materials decided they would go a slightly different way. And so we've got all these other wonderful looking materials. And this is the sort of thing that my wife would absolutely love, a bit glittery. Something here looks very much like these marbles or granites. These are not natural materials. They are full of a natural material called quartz. And if we look at the damaged edge on here, we can see the little crystal structure, the minute crystal structure. But this is not a stone. It's a man-made stone which is bound together with plastics and various other binding materials. And that's why I'm saying to you, we need to understand the materials that we're playing with, because some of these materials, which have got plastics in them, may produce nasty fumes. I mean, there's a very natural looking limestone material, but it's not. That's a man-made material. Simstone. I think the clue is in the name, simulated stone. We've got a large choice of materials that we're going to play with here, and we're going to find out which ones we could use to produce some nice photographs on. The question is, where do we start? Perhaps the easiest one to start with would be the slate. Now, this is a piece of slate that has been originally polished on this side, but because I've pulled it off the scrap heap, it's got quite a few scratches and dinks on it. But I think we might be able to see through that damage and be able to use part of it to put a picture on and see just what sort of quality we can get. What we're going to have to do is to actually do a few experiments to find out how this material reacts to different speeds, different powers. When we were doing organic materials, we tended to stay down at the 10, 12, 15% operating region for the laser, where we could get into this high frequency impact engraving zone where the pulses were very high. Subsequent to that, we've done some work with anodized material, and we found that we got good results by using something on this machine called special mode, where we were able to get pulsing all the way up the power range. So we might want to experiment with both of those modes while we're working with this material to see which one gives the better result. Now, before we start this work, I'm going to change this lens to something which you will probably have in your machine, or you will be able to put in your machine. Whether or not you've got this type of lens system, or whether or not you've got the lens system that I use on the light blade machine, where the lens is buried up in the actual lens tube itself, you should be able to use a 2-inch lens. But what I'm going to do is change it, not just an ordinary 2-inch lens. We found that when I was doing 3D engraving, we got some very good results with the 2-inch meniscus lens. And so I have got here a brand new 2-inch meniscus lens which I've bought. Now that 2-inch meniscus lens will produce more or less the same energy density as a 1.5 plano convex lens. Well, we found the ideal focus point for that particular lens. It's a 2-inch lens. Technically that should have a 19mm gap, but because we've turned it meniscus side downwards, which is the correct way, it shortens the focal length, and in fact this is ideally set to 17mm gap here. Let's do a little matrix test on here and find out how it marks. I have got some fumes coming off there, but I don't know what those fumes are. Okay, well now I've just literally changed the mode from standard common mode to special mode, and we'll run the same test again. As we've seen before, there appears to be virtually no power going through to the lens. Not entirely true. This is operating at 20,000 cycles a second, pulsing, and as a consequence this meter just cannot keep up with it. So it appears to be running very, very low current, whereas it's not. Okay, now we're going to go on to 65% power. At high speed, 400mm a second, the ammeter is just not registering anything at all. As it slows down to 300mm a second, we're registering a little bit more power. And in this last scan, I might expect to see it go up as high as about 5 milliamps, whereas it really ought to be up at somewhere around here at about 20 or 22 milliamps. Now it's quite difficult to see these, I think, but if I look at them from this point of view, and I'm at a different angle than you, first of all I can feel that this is particularly rough, but then again I can also see that it's got lots of little crystal structures showing on the surface. Here, no, that one. But we've got a choice, a wide range of choice there, because look, all of these are giving a good contrast against this dark background. So they're all suitable for engraving. Okay, well I've set it back to common mode now. We don't want to experiment with special mode until we get to the engraving side of things. We'll just find out what the material characteristics are. Now here we've got a piece of marble, as I said, calcium carbonate, limestone. And it looks as though it's got a sort of a glassy crystal structure to it. So let's just see what happens when we fire a pulse at that, should we? Well, that's interesting. It looks as though it's just burnt a little hole in it. There is a little bit of erasure on the surface there, but I don't know whether it's glass or not. There are just a few fumes here. You can probably just see the fumes in the air there. There are some as I get to these slower speeds and higher powers. Now, that's rather interesting. It's an interesting observation, because with that high power there, 100mm a second and 65% power, there's definitely some depth to that cut. Now it only might be 1/4 millimeter, but there is real depth to that cut, which is interesting. 3D. Let's see how limestone reacts, because that's basically a softer version of marble. We can see all the different tones on here, which is quite interesting. There's a little bit of depth to that one as well. And again, if we take a look, we can see that we are producing a little bit of very fine dust in there that's left behind. We're now going to go on to the granites. So the first thing I'm going to do is a 2-second pulse test. 0, 1, 2. We've definitely produced a little bulb of glass, clear glass on the surface there. Now we're going to try this rather expensive granite, which I'm told that these little teeny weeny flecks in here, these reflective flecks, are actually pieces, little flecks of copper. We'll do the burn test. 0, 1, 2. And that's produced a little bubble of glass there as well. I don't know whether you can see that, but this black stuff here has actually, with the slow speed at very high power, has actually turned to little, like glass beads on the surface. The same there. Not quite as much there. There's 1 or 2 little areas there where it has, but it's really pulled out in these areas here. Quite amazing. Granite doesn't look too promising a material to work with. Okay, so this is something called quartz. This is basically a man-made stone with, I suppose, inherently sand in it, but it is a material called quartz. Okay, so that's a bit different. That gives a burn mark telling us that we've got some strange sort of plasticky material there. So I shall be closing the lid once we get started with this, I think. It's interesting because I can actually brush all the black away. So dust of some sort. Burnt dust? I don't know. I can feel the quartz rough in the background, so really all we're doing is burning away the binding material, which is holding the material together. Now, I don't have any black simstone, and to be honest, I'm a little bit worried about putting anything really shiny like that in front of the laser. I've got no idea what that material is, but I suspect it's reflective. I know it's reflective to ordinary light, but I suspect it's a metal compound, and that will be reflective as well. My suspicion is that these are little flakes or something of aluminium that have been bedded into the surface of this material. As I hold that in the light, you can probably see all the sparkly bits there. Certainly at the top, but down at this bottom here, I'm going to take some of this black and put it in a plastic bag and look at it under the microscope, because I think that I might find little glass beads. Just rather interested in what this dust actually is. Now, isn't that a surprise? No little glass balls, just quartz crystals, but they've got black material on them, and that must be the binder material which is burnt onto the crystals. Now, when I held the pulse button on at the beginning, I was able to produce enough heat long enough to create glass, but obviously here we haven't had enough time to actually build the heat up and produce glass, just enough time to burn the binder off. There's a little teeny weeny bit of depth to that cut, but not enough to persuade me that we should even think about this as a 3D material. Summing up, granite, pretty useless. Certainly that colour, you can't see a thing. And that granite there, well, it's producing brown, look like beads of glass on the surface there, and a grey-white background. It's certainly all over the place as far as colour is concerned. And in fact, there's even some, when I look on here, I can see that's got like a silvery reflection. So I'm wondering whether we've got flecks of metal or something in there. I don't regard that as being a suitable material either. There's a really nice expensive black granite, but again, we've got this mottled effect in here of the materials in the background, the feldspar and maybe the quartz, and the quartz is coming up as little glass bubbles, by the look of it, little glass beads onto the surface. The textured finish in the background there is not going to give us a good white when we want it. The man-made simstone, which is basically quartz or sand with a binding agent, the white does not really produce a good enough black to be a good contrast, and the dark colour, which is this dark grey, does not give a bright enough white to give us the contrast that we're looking for. Marble was more interesting than I expected it to be. We don't have a good contrast colour in the foreground for photographic work. Interesting possibility here. It's only 1/2 mil deep, but hey, enough passes and we might even get some 3D marble engraving. And here we've got limestone. I mean, it's an interesting possibility to see whether we could do some 3D engraving on it, but I can't see it would be of any value because it's a very soft, useless stone. So the only thing that really offers us any promise at all is slate. Now, as I said, this is Italian slate. So what we can now do is move on to concentrating on just slate materials. I think we can start focusing on trying to get a picture onto this slate now, and then work our way through pictures on various other slates to see what the quality difference is in the pictures. Now, I'm just showing you the setup that I've got here for taking a look at the surface of these mineral materials. Looking at them straight on under the microscope is a waste of time because you can't actually see what's going on. We're looking at them at an oblique angle of about 45 degrees. I'm going to start off by taking a look at this granite because I'm not going to completely give up on granite at the moment, because there is a possibility I might be able to find a piece of less textured granite that I can work with. I can half imagine a photograph going onto here because we're not exposing large sections like we are here. We'll start off with granite and then we'll move on to slate, which was the only other viable material that we thought we could look at. I did say that I thought I could feel little bubbles or blobs of glass on the surface. I don't know whether you can see my arrow moving around there, but if we look in places like that, you'll see there and up here that we've got areas of what look like molten glass that have agglomerated together. We haven't got little blobs, we've got complete areas where they seem to have fused together. Because we're running slowly at high power, we've got obviously very high specific energy densities attacking this material. Now, if we increase the speed and decrease the power, we can basically go for a much softer energy density. Right, so here we are looking at 400 millimeters a second and 30% power. And at this sort of speed, even though I've got the increment set to, I think it's set to 0.15, we can actually see the scan lines here. But the great thing is, even though we can see the scan lines, if we take a look at areas like this, for example, down here, you'll see that as I'm running across this black material, I still appear to be having melting, because this is a glassy effect. This is reflection of the light that I'm seeing on this material. Even at 100 millimeters a second, 10% power, where we've got high frequency impact engraving, if we take a look down here at these lines, you can see the way the light is striking them, it looks as though we've still got some sort of melting taking place down each one of the scan lines. Even though we've got high frequency pulses going on here, we've still got enough power to melt this material, which is quite amazing. But I think you can see that we're not really disturbing the crystal structure of this white material. We're not doing any damage to it at all by the look of it. And because I can't see any evidence of chipping or damage on this white material, it looks as though we're likely to be evaporating it rather than sharding it. Okay, so now we're going to take a look at the slate, because I think this offers the best prospect for our engraving. Now, this is the 2 or 3 second burn test that we did, and here you can clearly see the little volcano that happened, and right round the edge of the volcano there we've got a little ring of glass that has formed. Now in the foreground you'll see there are some cracks, so obviously there's been some heat stress in this material which has caused the beginning of a flaking effect. So there's several things I'd like you to look at on this picture. First of all, we're running at 10% power and 400 millimeters a second, virtually as fast as we can go and as lower power as we can go. But we're still marking the material. Because we're in the 10% pre-ionization region, we've got high frequency pulsing going on. And if you look at the lines, you'll see loads of little teeny-weeny black dots in the lines where we've got the pulses. In addition to that, the line spacing is 0.15, and you can see the gaps between the lines. And it looks as though those lines are down at around about 0.1 wide,
which is very promising for getting very small dots. If you look at the ends of the lines, you can see the scan line offset because we're running at high speed. Now, it's something that you just can't see on these pictures, but I can see with the naked eye, and that is that these are not scratches. These are little high temperature pulses that are actually converting this slate into a glassy material. So it's turning it into a grey glass. So each one of those little black specks represents a little volcano, and we are producing a little bead of glass at each one of those specks. So we're turning this material on the surface into a glassy material. It's no longer slate. As we increase the power, let's go 400 millimeters a second and 30% power. Now we've got steady power. We've no longer got pulsing. But we appear to have little blobs. But that's because what we've got are little blobs of glass that are amalgamating together. We've still got fairly good definition along the lines, the scan lines. But bearing in mind this is now 30% power. So we're probably at something like about maybe 40 watts that we're throwing at this surface. When we start and stop at the end of the lines there, you can see that there isn't the offset that we saw when we were running slowly. The main reason for that is we've got so much power there now that when we start slowing down right at the end of the stroke, we're actually burning a little pool of glass. So there's virtually no difference between the start and the finish because it's all melded into one little blob. And you can see the blobs disappearing as we accelerate away and we get up to full speed because the lines start appearing. And now here we are at 65%. Now when you look at that picture, it looks like a piece of knitting, but let's look at it and try and analyze what you're actually seeing. Starting from the right, you can see that the first line is not in line with the return line, and that's because of the response time of the high voltage supply. It's the same offset that we saw when we were running at very, very low power, but of course this time the line is very, very thick. If you look at the second line, you can begin to see what's actually going on. The second line has got a black piece down the center of it, and that's because the beam is cutting in really deep, and what we're doing is creating a little volcanic eruption. We're causing glass to be formed on either side of the channel. And so the whole of this surface, when we start looking at it, you can see they're little bubbles of glass that are amalgamated together. Now you just can't see that with this microscope, but with the naked eye you get this lovely clay grey glass that's formed on the surface. Now this looks interesting because it's the fastest speed possible, 400 millimeters a second, at the highest power, about 65%. And look, we've got thin lines, we've got lots of dots because this is done in special mode. I mean, that's 300 millimeters a second, that's 200 millimeters a second, and that's 100 millimeters a second. Well, as you can see, at 100 millimeters a second we're definitely getting glassy blobs. Even in special mode we're generating too much power and we're producing glassy blobs on the surface.
Thank you very much for your patience, because it has been a little bit of a boring session in ways, because we've had to research the materials themselves that we're going to work with. We could spend a great deal of time just throwing parameters at various materials, and some of these materials, as we found, are just not suitable for the sort of work that we want to do. They may be great for engraving logos on, where you've got enough contrast that you will be able to, use the dark surface against the interesting background. But for photo work, this granite is not a suitable material. I have to say that this slate has been the biggest surprise for me today, because although normally you'd expect to do this with a piece of granite, you produce a scratch on it and it comes out with a nice grey background. But this grey here is nothing to do with scratching or damaging the surface. Is conversion of the mud or the silt or the clay that's underneath it, basically a silica material, converting it into glass. Now with these low powered ones on special mode, we're only producing a very thin layer of glass on the surface, and it doesn't take very much to scrape this glass off and get to the layer underneath. That's because basically it's a bit like building a house on sand. There isn't very much of a firm foundation for the thin crust of glass that's sitting on the top. But when we get to these common mode, we're using very low speed and very high power, where we've put a lot of heat into the surface and we've produced quite a thick layer of glass on there. That is quite a stable material. Now, it's interesting to know the difference, because if you want to do, for instance, portrait work for inside jobs, then this is not going to be a problem, and you can use these very lightweight material, this very lightweight etching, because really all we want is the colour of the glass. It produces a nice uniform colour against the black background, whereas here we need a thick layer of glass if we're going to do things like logos or house names that are going to sit outside. So this has already been a very interesting and revealing lesson to me, and we haven't started to engrave any pictures yet. So that's the reason, that's one of the reasons why this has been so useful to me. But for photo work, I have found a piece of, from the crystal structure on the edge, this is definitely granite. But it's quite a nice, even textured, black, greyish granite. I think I might have some success with this as well. So until the next session, when we'll get stuck into some dithered photo engraving, thanks for your time.